Welcome to our webinar. Thank you for joining us. Today, we're very pleased to present to you XSite version 4 Unleashed, speaking about hydraulic fracturing in naturally fractured reserves on high-performance clusters. Today's presenter will be Dr. Branko Demjanov, who is a principal engineer at ITASCA, Minneapolis. He has experience in the design and analysis of underground excavations for oil storage and waste isolation. He has been involved in stability analysis of underground and open pit mines in both hard and soft rocks. Branko has developed a 3D numerical model to simulate the coupled hydromechanical response of fluid-saturated rock mass. He was involved in a number of projects in petroleum, geothermal, and mining industries with objectives of design and operation, optimization of rock mass treatment by fluid injection. So we will be taking questions today. We would ask that you save your questions for the end of the presentation, but you can submit your question at any time. In Teams, if you click on the Q&A icon at the top of your Teams user interface, you can simply type in your question and submit it. And then we will read those out at the end of the presentation and answer your questions. We will be posting a recording of this presentation to our YouTube channel. Anyone who's registered for the webinar will receive a link. Thank you. Branko, please proceed.
Thank you, Dave. Hi, everybody. Thank you for joining the webinar. The main focus of talk today is using XSite on high-performance computing clusters, but I will start with some general introductory descriptions for the sake of those who are not familiar with XSite, but also to remind maybe those others who know something about it. So XSite is a numerical software for simulation of treatment of naturally fractured rock masses by fluid injection, and these technologies have been used in several industries, in oil and gas for a decade, and more recently in geothermal and even in mining for reconditioning of the rock mass. Important feature of XSite is that rock mass is represented using the synthetic rock mass method or approach. And in XSite, synthetic rock mass or SRM is implemented in the lattice model. So what is synthetic rock mass? So any code that has capability to explicitly represent pre-existing joints as discrete features and their deformation, slip, and opening, but also in addition to that, simulate fracture propagation in the rock bridges, in the rock matrix between joints, basically implements or models using a synthetic rock mass approach. First implementation of the synthetic rock mass was in another ITASCA code called PFC. And in PFC, the intact rock mass was represented by a bonded particle model. And we found that bonded particle model quite well represents the mechanical behavior of brittle rocks, deformation, and cracking. Basically has capability to simulate fracture propagation in the intact rock. Lattice is a simplified version of the PFC. Now, if we represent the discrete features, pre-existing fractures, using smooth joint model in this bonded particle model, we have what is illustrated here in this slide in the middle, a synthetic rock mass representation. The fracturing in the synthetic rock mass model can be represented using discrete fracture network or DFN, which matches the statistical characteristic of the random fracturing in the rock mass, or the fractures can be represented as discrete features with actual geometry and the location. So what are the advantages of the SRM or synthetic rock mass? It is mechanics-based approach, and consequently, it represents dominant mechanisms of the formation and the failure of the fracture rock mass, which very often consists of sliding and opening of pre-existing joints, and fracture propagation through the rock bridges between these joints. And finally, the SRM can use the results of standard testing methods on small scale samples, and then automatically, if we have correct representation of the FN, automatically accounts for the scale effects. In contrary to the typical approaches in rock mechanics, where we use some empirical formulas to upscale the laboratory properties to the field scale. The lattice is a quasi-random array of the nodes and the springs in the 3D. So here in this cartoon, I'm showing you the representation of a lattice in a 2D. One important thing to notice that this cartoon is missing is that actually each node is connected by two springs. One normal as shown here, but then there is another one which is a shear. So internally, lattice or XSite execute the calculation in terms of deformation and a failure of these springs. However, the properties of the springs, which sometimes don't have physical meaning, are automatically calculated or calibrated to match typical engineering properties that we are used to work with, like Young's modulus, Poisson ratio, tensile strength, or a toughness. The reason that we use lattice in XSite instead of, let's say, particle flow code type of formulation is that lattice is more efficient and allow us to simulate the problems with can have up to 10 million particles to standard personal computers. Now, the lattice resolves and models the mechanics, deformation, and the damage of the rock. But for simulation of hydraulic fracturing, another important component is the model for fluid flow. And the model for fluid flow is directly related to the mechanical model or the lattice. So in the flow model, particularly when we simulate the flow in the fractures, we assume that microcracks are created every spring of the lattice, which is intersected by pre-existing joints, or which is failed during the simulation. The crack in the flow model acts as a reservoir, and we keep track of the pressure for each of these reservoirs. The microcracks, which are within certain distance, are connected by pipes, which then allow for pressure dissipation and a flow through the network of the fracture. So important thing to understand is that the flow model and mechanical model are directly connected, and the geometry of the flow model evolves as a function of the evolution of the mechanical model and the damage of the mechanical model. In addition, the mechanical and flow models are fully coupled, meaning that the fracture permeability depends on the aperture, or in other words, on deformation of the mechanical model. On the other hand, the fluid pressures affect the strength, and changes in fluid pressure also cause the deformation of the mechanical model, while in the same time the deformation of solid model affects and causes the changes in the fluid pressure. So what are the advantages of XSite? Like number of different software tools available currently for simulation of hydraulic fracturing, XSite doesn't make any general assumption regarding the fracture trajectory or a fracture shape. It resolves general interaction between multiple hydraulic fracturing, resulting in models that can show fractures deviating, attracting each other, or deflecting. Also, XSite can simulate general interaction between hydraulic fracture and pre-existing fracture or joints, where those joints can result in arrest or deflection of the joint of the hydraulic fracture. So all modes of hydraulic fracture, pre-existing joint interaction can be reproduced in the XSite. So XSite has a unique capability to simulate hydraulic fracture propagation in heterogeneous and fractured rock masses. So here In the next couple of slides, I will provide overview of the capabilities of XSite. So there are two versions of the code, Linux and the Windows. The code comes with a graphical user interface, which is convenient and easy to use. So the code is special purpose code developed just for simulation of hydraulic fracturing. On the other hand, in the Linux, there is also console version which actually can allow more efficient execution of number of models on high performance computing centers. So GUI allow basically inspection of the model and the model geometry and the results and their manipulation and presentation in different views in a 3D using graphical interface. The models can be set up in local and global coordinates. The advantage of global coordinates is that in one particular geometry, in terms of faults, wells, and so on, the XSite model can be automatically moved to a different location without redefining the problem geometry. It comes with number of built-in rock types with different properties, and these rock types can be also expanded during the use. It allows different ways of initialization of in situ stresses and fluid pressure fields, starting from relatively simple, uniform with a constant gradient, but it also allows importing of the pore pressure and stressor field that are already affected by well production, which is very convenient for simulation problems that involve the parent-child well interaction. It explicitly represents pre-existing joints, and there are a number of different ways that these discrete fracture networks can be defined, or they can import it from, as created by other software tools like Fragment, for example. The code can include and simulate arbitrary number of wellbores and injection points, or there could be either perforation clusters, open holes, or explicitly represent perforation. It can simulate synthetic microseismicity, which is very important capability for model validation and calibration with the field data. It can simulate non-steady flow in a fracture network, but also in the matrix, and the flow in the network, fracture network and the matrix is fully coupled. On the other hand, since that is typically used in oil and gas industry, we can also simulate a leak of using Carter leak of calculation. The purpose of the model of matrix flow is to have general model for simulation of the leak of, but we can also represent the leak of using the Carter leak of calculation. The code includes the logic for simulation of proppant transport and the placement. It can simulate Newtonian and power law fluids. It can account for non-Darcy effects and also represent the pressure drop, the cluster, using the empirical formulas from published literature. It has capability to simulate different modes of heat transport, including conduction, advection, and convective heat exchange. And of course, these capabilities are very convenient for simulation of, geothermal operations. Each of these simulation modes, flow, mechanical, or heat transfer, can be done either coupled or separately. So you can just run model to mechanical equilibrium, or you can run the model for steady flow. And also, the code includes different coupling modes for simulation, where we can actually do tightly coupled processes, where all processes are done, basically every step, and coupling is two-way. But then, for sake of computational efficiency, we can carry out couple processes where we do it more efficiently, where some of the processes are advanced in time much faster, based on assumption that, let's say, the mechanical model is in some kind of quasi-static, quasi-equilibrium state, or fluid flow model is in a steady state. And then, in terms of convenience of running models, a model can execute on a single node or on high-performance clusters, and that's something that we are going to talk a little bit more today. And when running models on high performance computer clusters, we can actually take advantage of distributed memory parallelization, where the same model can be executed on multiple computer nodes. And that parallelization is implemented using MPI libraries. Of course, during simulation, the model state can be saved at different stages, and those saved states can be used to review results during the simulation, but then also can be used to restart model at a later stage. The model can be run fully interactively, but also in a batch mode, and all simulation steps are predefined at the beginning of simulation, and then the code executes all steps automatically. The units used in the model matrix, so we basically use two sets of units, matrix sets of unit and oil field units. The results can be output in different in various form and different graphical formats and file outputs. For the sake of optimization of the model, there are different ways to discretize the model using basically graded resolution, where fine resolution is used in the areas where the most of the pressure changes are occurring, and coarser resolution is used away from to provide the proper far field effects. But then in the models where we have the multiple stages in the same model, we can actually code allows remeshing, where we actually move that fine resolution domain in the areas where the current stimulation is occurring. And we can also import the geometry of the geology of the structures using the DXF file in different and other file formats. And then the results of the model, typically the condition of stimulated permeability, can be then upscaled and exported and used in other codes, reservoir simulator, to simulate production or long-term circulation. Although in some general cases, XSite can be as well used for those long-term circulation operations. So today we are talking about use of XSite on high-performance clusters. So now, first time, the capability to run XSite and take advantage of distributed memory parallelization using MPI libraries is commercially available. So with this capability, the one model can be run on clusters of computers, and the model is run more efficiently by decomposing and running different parts of the model on multiple computer nodes. That decomposition in XSite can be done either manually, where the model is geometrically divided in number of parts in each coordinate direction, or the decomposition can be done automatically using a Metis library. The code internally, as I mentioned before, has different computational modes. So it can run hydromechanical couple problem, it can run THM type of problems, or only mechanical. So all these computational modes are parallelized in XSite. So one way of taking advantage of these high performance clusters is doing distributed memory parallelization, which gives us advantage of faster execution of one particular model. However, there is another way of taking advantage of these high performance clusters in XSite, where for the XSite actually can facilitate automatic execution of sensitivity analysis. So in the problems in geomechanics, there is quite often uncertainty with field conditions, which warrants sensitivity analysis in terms of some of these uncertain input parameters. So XSite has a capability to automatically execute these sensitivity analysis on high performance computing centers, where it actually runs different model instances on different cluster nodes. So important thing is that when these sensitivity analyses are set up, the user can specify which of the input parameters are uncertain or are provided as statistical variables. For example, the user can specify that in situ stress and Young modulus and let's say DFN are uncertain. And then for each of these variables, for example, for Young's modulus, it can provide the mean value and standard deviation. For the DFN, user can provide the multiple realizations. And then the code will automatically, based on those input parameters and the specified number of simulations that need to be executed, will select different realizations by picking from those distributions. And then it will also automatically then send each instance of the model to different nodes. The code will then also be able to follow and monitor execution of each of those models. And then upon the completion, do some compilation of the results, and the user can specify which of the results need to be compiled. So here is the simple example that is used for benchmarking of MPI parallelization. So we are specifically looking at performance gain, and then also we look at the model results. So the model that is used here is relatively simple. It has two injection cluster, three pre-existing joints, which are shown as these transparent disks. And actually, for this benchmarking test, we actually use in this model the resolution which is much finer than it's really needed, because we really wanted to have a representative simulation time. Running this model with the resolution in this particular case took something like 19 hours. Of course, this example can with the proper resolution can be solved much faster, probably of the order of 15 minutes. And again, this example includes running model in different modes. So first, equilibrating for the initial stress, then simulating injection in one cluster, resetting pressure, equilibrating again for reset pressure, and then running injection in the second cluster. Anyway, and then we run the model. In this case, we actually used manual model decomposition. So we ran the model where, let's say, in the second instance, we actually used 4 nodes, and decomposition was 2 segments in the X direction, 2 segments in the Z direction, and it was 1 in Y direction, resulting in, so basically the model was divided just geometrically in 4 parts. So each part was then executed on a separate node, but of course the execution is done fully coupled with communication continuously, with information continuously communicated between different nodes. So here in the table, again, we show the simulation time and the computation performance gain compared to the single node as a function of how we decompose the model and the number of computer nodes used for the simulation. And the results of the performance gain as a function of number of nodes are also shown here in a chart. Of course, this type of trend is expected. The performance gain cannot be linear as a function of number of nodes, but what we see is that the relative gain decreases with increasing number of the node, which is expected because there are losses on a transfer of information between these different nodes. But we do see that, let's say, for 64 nodes, we have gains which are greater than 10. In this particular case, 13.2. And we also expect that with Mattis library, these gains will be even better. And then the other part of the benchmarking and verification of the implementation of the MPI's comparison of the results. So here I compare or show the results of induced cracks. So these blue dots are basically induced micro cracks by the fluid injection, and we compare here the results for single node and 64 nodes, and we see that for all practical purposes they are the same. They are not identical, and again, this is the same thing as if you run different model with slightly different discretization or different mesh. There are small changes, but they are completely negligible. So, and there is this again comparison of the apertures induced during a simulation between these two models, one with a single node and one with 64 nodes, and we see that results are almost practically the same. So next I'm going to show you two applications of XSite, and in both of these cases, again, the models were run using high performance computing clusters, and both examples were done for the FORGE project, which is Frontier Observatory for Research in Geothermal Energy. This is a DOE funded project. It is located in near town of Milford in Utah, and the purpose of this project is to develop new technologies that would make geothermal energy economically viable. So the first problem, we focus on modeling of fracture initiation from a perforation cluster, and this is very important problem because the fracture geometry and its tortuosity in the near field of the well and perforation is very important because it affects the pressure drops and pressures required to propagate the hydraulic fracture, and even more importantly, the pressure required to circulate the fluid, let's say during the production phase, and also it affects how the proppant is transported and placed. And so in this model, since it's a near wellbore model, we are capable to represent the detail of geometry of the well and the perforations. In this particular case, so in this plot in the bottom right corner is shown the well trajectory. So this is the injection well 16A. As you can see, it is highly deviated well, 65 degrees from vertical, and the particular stage that or a cluster which is simulated in this case is stage 4 out of 10 that have been completed so far. So the dimensions of the model is basically the model is a cube 6 meter at length. The stresses are initialized so that although in the model the well is represented vertical, the stresses are initialized to exactly correspond to the stresses relative to the well in the actual conditions. So the perforated section is 6 feet long. There are 6 shots per foot with a total 36 perforations phased at 60 degrees, and we actually represent the casing cement. So it's 7-inch casing, 8.75 inches borehole. And if you're more interested in this problem, it's actually described in the paper indicated in the bottom left corner. So we show the results here, and in this particular case, we assume that there is no DFN in the reservoir or in the rock mass around the well and the perforation. So we show the results at different stages at very early times during injection, and here on the upper left corner show the history of the injection pressure, and as a reference, this blue and red horizontal line are basically bottom hole pressure estimated based on the surface pressures. In one case, assuming that there is assuming friction in a borehole, and in the other case, just assuming the hydrostatic pressure. And so the black line is the model result, and we see that the breakdown pressure actually falls between those two lines of the breakdown pressure estimated from the surface pressure. On the right, we saw a side view of the showing the well and perforations and induced micro cracks. But then we also showed the model in the vertical cross section with zoom in detail. So if you look at this, you can see interestingly that the fractures initiate from perforation, but we also see that the finite strength of the cement has a significant effect. So the cracks actually also propagate through the cement and also in the interface between the cement and the rock. And in this slide, so we show the results from the same model at in three additional times. So on the top, we are showing again side view where these different colors actually correspond to the cracks initiated from different perforation tunnels. And then on the bottom, we show the geometry of the fractures, but in a plan view. Yeah. So what you can see is that as the injection progresses, these fractures initiated from perforation tunnels coalesce and then actually create the fracture which is actually along the well and perpendicular to the SH max, which is intermediate principal stress. So, but then at the later times, what you see is then that at the end of the perforated section, the fractures start turning into the direction perpendicular to the minimum horizontal stress, which is along the direction of the well and the horizontal, of course. And then final state, again, showing in a side view in the middle, and then here it's the rotated view of the induced fractures from these perforations. And just for a reference, we show here the picture from the lab experiment showing the induced fractures from the perforation cluster. And there is a remarkable similarity between the model results and this lab experiment. And the model does show the level of complexity and the tortuosity in the fracture geometry in the near wellbore environment. So this example was done in the model where we assume that rock mass is a massive homogeneous without any pre-existing joints. There is another similar example in which we actually assumed that there are pre-existing joints and studied the effect of this DFN on a fracture initiation. So those pre-existing joints in near wellbore environment are indicated as shown as these polygonal surfaces, transparent polygonal surfaces. And on the left, we showed the simulated injection pressure at early times. And on the right, we showed the geometry of the induced fractures at these different states. So what we see in this slide, we show the state A. So what we see is that at state A, we had a breakdown. A breakdown occurred because one of these perforations reactivated one of the DFN fractures that intersected the perforated section of the well. So, and as the fracture got reactivated, the pressure dropped. However, what we see that in this region, actually, the fracture intensity is quite large, and these other pre-existing joints actually arrest and prevent further propagation of the fracture from that pre-existing joint, and that resulted in the pressure increase. And that is a typical observation that sometimes actually DFN results in increase in the injection pressure because the hydraulic fractures get arrested. So if you go to the next slide, what we see is then as the pressure increases, it increases enough to then reactivate another pre-existing joint oriented probably at less favorable orientation than the first one. And as that joint got reactivated, we see the pressure drop, and then subsequently pressure start increasing. However, Now, from this joint, you see that this joint, pre-existing joint, is kind of isolated, and then it allowed the fracture initiation or fracture propagation, further propagation, but now propagation through the intact rock and in direction of the far field, the minimum principal stress. So these two examples kind of show how XSite can be used for basically simulation of fracture initiation and can include quite complex geometry, both of the well and perforations, but also it can include the pre-existing fractures and help understand how those pre-existing fractures affect the fracture initiation from the perforation cluster. So the other example, again from the Forge project, but in this case we actually looked on fracture propagation from multi-cluster stages at the longer time scales and on the reservoir scale. So in this case, we looked at the injection times of the order of a couple of hours. So because of the different scale of the problem, we don't have luxury and cannot represent all details of the well and perforation geometry. Instead, we basically assume that in these large-scale models, we assume that the fracture has already initiated, and we assume that it has initiated in the direction perpendicular to minimum principal stress. All details of the fracture tortuosity and perforations now are abstracted. However, their effect can be accounted for in basically perforation pressure drop, which is implemented in the code using some empirical formula. So you can see that this model that is used for simulation of hydraulic fracture propagation on a scale of reservoir is a cube with 600 meters edge length. In this model, we explicitly include almost 18,000 fractures, which are kind of illustrated in this plot. And on the Forge project, those fractures or discrete fracture network are stochastically generated based on data obtained from mapping the borehole logs and using some information from the microseismic data recorded during some of the initial stimulation stages. So in this model, the fracture size varies between 100 and 150 meters. And of course, there is a lot of uncertainty in the hydromechanical properties of the DFN. And the one thing that we did on this project was to calibrate this model by varying these DFN properties, the strength, permeability, and so on, in order to match the recorded injection pressures, the fiber optic data, and the microseismic data. So I'm not going to go in detail about the model calibration. I'll just say that actually we observed quite good match. And if you want to read about more about the results and modeling, you can actually, it is published in the reference which is provided here in this slide. I just want to show again, some of the results from this model. And what I really like here is that it kind of nicely illustrates how the DFN affects the hydraulic fracturing, or how hydraulic fracture interacts with the DFN. Now here I'm just showing a couple of views of the model results, and in order to be able to see anything, because the model includes all these DFN fracture and so on, we show the results in a clear box, which is kind of centered around stage 8. So these different stages and injection clusters on well 16A, that is actually stimulation well, are kind of indicated here. And then this plot on the left side actually shows only induced micro cracks, but you can see how those micro cracks relate to pre-existing joints, which are shown again in this slide as these transparent polygonal surfaces. You can see that fracture propagates, get kind of diverted into pre-existing joint, and then reinitializes from the edges of that joint. And these two other plots kind of show similar thing, except that the one on the right shows both the hydraulic fracture and the DFN and the contours of the apertures in both hydraulic fractures and in DFN, while the one in the middle kind of differentiate the DFN because it shows the apertures, but then hydraulic fracture induced micro cracks, or hydraulic fracture is again shown as purple squares. And then same model, same result, just different view. So you can again see that, you know, some of these pre-existing joints are actually part of the fracture induced fracture geometry, and the model actually shows exactly what is observed from fiber optic data, that the fracture doesn't propagate vertically upwards. Instead, the DFN affects the fracture trajectory, and its propagation kind of moves towards the heel side of the well. Okay, so this is what I have prepared for today's webinar, and would be happy to answer questions if you have.
Great. Thank you very much, Branko. We do have some questions. Let me just pull them up. So the first question is, out of interest, Branko, what can't XSite do? Because this list is pretty much infers it can do it all. I think that referred to an earlier list in one of your slides.
Well, I mean, I think XSite has a really wide range of capabilities. So what it cannot do is it cannot give you results in 15 minutes. So the numerical tool with capability to include all physics and also include high level of detail in terms of geology and so on comes at the cost. We are very well aware of that limitation, and we work hard to improve the computational speed and the capability to take advantage of distributed memory parallelization. I mean, that's one of the things that we are doing, but we're also looking at improving the algorithms, coming with different computational modes and so on. So basically, we try to take advantage of any and every simplification which is justified and acceptable. But we don't make assumption that fracture is planar. We don't make assumption that DFN doesn't affect fracture propagation, because in general case, neither of those are correct.
Okay, so the next question is, what is the difference between manual and METIS, METIS, automatic decomposition?
So in a manual decomposition, as I try to explain, the user will basically say, okay, so let's say that the edges of this model, this cube, are in 3-coordinate direction. The user would say, okay, I want to, when I run this model at HPC, let's say I have 24 computers available. So when you do manual decomposition, you can say, okay, I want to divide my model in 3 parts in the X direction, in, let's say, 4 parts in Y direction, and in 2 parts in the Z direction. So if I did my calculation correctly, that would give you 24 domains, and then the XSite would do this decomposition of the model, automatically assign each part to different node, and then the model will be executed, you know, where these nodes would be running in parallel and communicating information to preserve and maintain continuity and so on. With the METIS library, you basically say, I want to decompose model in 24 parts, and then so the problem with manual decomposition depends how you discretize the model or whatever. Most likely, each node will not, the computational load will not be balanced or evenly distributed between the nodes. And the problem with that is that the nodes which have less computational loads will be sitting and waiting, and that would, on the other hand, nodes which have most computational load would be basically nodes that would dictate simulation time. With the latest METIS library, actually this decomposition is done automatically, and the Mattis library allows you balancing of that computational load. So Mattis library will ensure that the composition in 24 nodes will be done in such a way that each computer gets same computational load.
Great. Thank you, Branko. Next question. Could you elaborate a bit on adaptive resolution? Is it like the ARM in FEM? And I assume that's adaptive mesh refinement.
Yeah, so basically adaptive resolution means, let's say that you want to simulate 5 stages along a lateral, and when you simulate particular stage, you really don't need to have, so you need to have fine resolution only around the stage which is currently active. You don't need that fine resolution around the stages that you simulated previously or you plan to simulate in a future. On the other hand, you need to include all of those stages because they provide the boundary condition, let's say stress shadow effect, and so on. So the adaptive resolution is basically remeshing. So once you finish one stage and you move to the next stage, then the XSite will basically recreate a new lattice where basically the finest resolution domain will be now around the new stage, which is currently active. However, the code will not do only remeshing or recreation of the lattice. It will also interpolate all fields from the previous state. So you would have a continuity of all fields in the model, but the model will continuously remesh to have the finest resolution where you need it, but then also to optimize the model size so you don't have fine resolution everywhere, even at the stages where you don't need fine resolution everywhere in the model.
Thank you, Branko.
Sure.
Next question. It goes, hello, Branko. Very interesting examples. Thank you. In the large-scale forge model, how do you account for the geometry uncertainty associated with the DFN?
I mean, the only way to okay, so for that reason, when we look at these results and we compare them with field data from fiber optics, fracture hit, our model does not exactly match the basically fracture hits in the second well, in the production well, which is indicated here as this upper line. And the main reason is because we use stochastic DFN. On the project, we tried to make it as deterministic as we can, but we can do that only around those wells which are mapped or and in vicinity of the wells. So so what is important then is that the model qualitatively matches the response and the trends. But again, because the DFN profoundly affects the fracture propagation and DFN is stochastic, we cannot say, okay, the model will predict exactly where the fracture hit is observed. The only way to deal with this, if you are trying to predict or would be again what we mentioned in when we talk about capabilities to execute sensitivity analysis. The only way to deal with this would be to generate or create the stochastic DFN and then use multiple realizations, run multiple models, sensitivity with respect to DFN realization, and then obtain the results of possible trends or so it just cannot, if you are using DFN as a stochastic input, the result also cannot be deterministic. Best thing you can do is do sensitivity analysis, and then you get a range of responses. And yeah.
Thank you. There's a second part to that question. With respect to the forge model, how many elements did you have in those models, and how long did it take them to run?
So I apologize, I don't have information on number of elements. We can provide that, but this model took 2.5 days for, I think, 70 minutes of injection time.
Great, thank you. We have the person who asked that question, so Yvonne, we'll follow up with you on that.
Okay.
Next question. Maybe I missed this, but does XSite include perforation and/or formation erosion and proppant transport?
So XSite does include, okay, so as I've shown in this example, if you want to do near wellbore model, you can actually represent perforations explicitly. If you're doing reservoir scale modeling, again, the mixing of the scales would make that would allow you to represent perforations, but then also simulate something on a scale of hundreds of meters and so on. And to make model incredibly large. So for that reason, when we do, simulation of hydraulic fracture propagation on reservoir scale, we don't represent explicitly perforations, but we can actually account for the effect of perforation by including the perforation pressure drop. And that is very important thing, like to model limited entry and distribution of the fluid between different perforation within the same stage and so on. The code, yes, the code can simulate the proppant transport and proppant placement, and it can simulate fracture closure on a proppant and also the effect on proppant on induced permeability and so on. So, Dave, was there any other part of the question that maybe
Formation erosion?
Oh no, so we don't account. Yeah, the model doesn't account for formation erosion. No.
Thank you. Just a few more questions. I think there are also limitations on the type of frac fluid, i.e. incompressible only, and on the type of rock failure, i.e.
Yes.
brittle only. Is that correct?
Yes. Yeah. So
Okay.
it's XSite assumes incompressible fluid. My apology, I didn't mention that. It assumes incompressible fluid, and the lattice and the bonded block model are good models for simulation of the deformation and damage of brittle rocks. Correct.
Okay. Thank you. And then there was a question, is load balancing dynamic now? But I assume that's what the development that's currently ongoing.
Load balancing. Okay. So, yeah. So load balancing cannot be done during simulation. However, each time you stop the model and you restart new stage of simulation, the load balancing can be improved or redone. And in some models, probably that dynamic load balancing shouldn't be important, but in XSite it is, because the model geometry changes. Because as the simulation progresses, the fractures propagate and so on, and those fractures, of course, involved simulation load and so on. So doing load balancing during simulation at different stages is useful, and that's what Mathis will allow. But we cannot do it as the simulation is going on. It can be done only when the model stops, you save it, and then you continue next stage.
And Branko, will the new Métis library, will that do that automatically in the future?
Yes.
Or did
Yes.
Okay, great. Two more questions. You mentioned simulation for the forge example took 2.5 days for, I think it was 17 minutes of injection. I'm curious how many cores.
No. I'm sorry. It took 2.5 days for 70 minutes of injection.
Oh, 70. Sorry, that's my mistake. The question had it correct. So 2.5 days for 70 minutes of injection. Curious, how many cores did you run that model on?
I think I'm sorry, I don't know exact number.
Yeah.
I believe 27.
Okay, thank you. Great. And then the last question is in the chat. Oh, no, sorry. My mistake. They re-asked the question in the Q&A section. So that is all the questions. So thank you very much, Branko. Thank you for everybody for joining us today and seeing all the new exciting developments and capabilities in XSite. If anyone is interested in a free 2-week trial, please contact us at sales@itascasoftware.com, sales@itascasoftware.com. If you'd like to set up a discovery call and talk about the software or your project, please also contact us at that same email, which is also in the chat. Great. Thank you, everybody. Thank you, Branko. Have a good day.
Thank you, everybody.
Bye-bye.